So let me start off where I'm left off. When I left off in the last lecture, I gave you all these problems, and I showed you how to solve the problems by taking a velocity versus time graph and using that to determine various unknowns. Relating that on the velocity versus time graph, the area underneath gives you the change in position, and that the slope on the velocity versus time graph would give you the acceleration. So we can get a lot of information just off of that graph. In fact, sometimes all you need is that graph. In other cases, you may not know the time it takes that it's moving, or you may not know the final velocity, in which case then you're going to need a bit more information. You can get that from the acceleration versus time graph. Okay? Now we get to do a little bit of algebra here. You see, what happens is, if we keep having the same kind of motion, then we're going to keep the same kind of graphs. In other words, if we have something that's constantly accelerating, it's going to have a straight line on the velocity graph which has some kind of slope. What that means is that we're still going to find the areas, we're going to still have triangles and rectangles over and over and over again. We're not getting anything new. We're just still getting base times height and 1/2 base times height. We're going to start seeing the same equations over and over and over again. Or we're going to start building the same equations over and over again. So tell you what, let's go ahead and skip that. Or what I mean to say is, let me go ahead and derive what those equations are going to end up being. Then we might be able to skip the graphs, although the graphs certainly will help out. Now, how are we going to go about doing that? Well, here's how it works out. We're going to make a couple of assumptions here for our motion. Assumption number one is that the acceleration is constant. Okay? We're not talking about changing accelerations like you would find on a drag race. In a drag race or in a sprint race, you know that you've got to have a lot of acceleration at the very beginning. The acceleration, it goes down as you continue to speed up. You're just speeding up slower. Okay? That's one assumption. The second assumption is going to be a notational assumption. Where we have delta t before, the time interval, which will be t final minus t initial, what we're going to do is we're going to assume that we're taking the time with a stopwatch. That means the t initial is always going to be 0. So what's t final going to be? The answer is whatever I read on the stopwatch. So t is now going to replace delta t. T is going to represent what I read on the stopwatch if the initial time is 0. Does that make sense so far? Okay? One more thing, and I'll explain it to when we get to it. Let's start off with the acceleration versus time graph. Let's start doing the derivations here. What we're doing is we're creating a mathematical model of constant acceleration. Okay? On the acceleration versus time graph, we see that the acceleration line is straight horizontal across. It's going to go across for however long, it's some period of time. Okay? What's the area underneath the acceleration versus time graph going to give me? The change in the velocity, correct. So therefore, since the area is equal to the change in velocity, the base is the time interval, delta t, and the height is the acceleration a. So I can write v minus v0 equals a times t. Now here's my next notational assumption here. v0 is going to represent the velocity at time 0. It does not mean 0 velocity. It means what was the velocity of the object when I started the stopwatch. Anybody who's ever seen barrel racing or NASCAR driving, you know that there's going to be an initial velocity when they start the race, yes? When they cross the start line, they're moving. So we cannot assume that the initial velocity is always 0. Okay? Sometimes we can. A drag race or a sprint race, now the initial velocity is 0. V then represents the velocity at whatever the time on the stopwatch is. Time 1 second, I'm going to have a certain velocity. Time 2 seconds, I'm going to get a certain velocity. Time 3 seconds, I'm going to have a certain velocity. In other words, I am making a function here. V becomes a function of time. And that's why I don't have a VF. because if t changes, v is going to change. Does that make sense? Okay, we're going to run with it. Simple. I'm going to do some algebra here. Don't be frightened. I'm going to get rid of the negative sign. How do I get rid of the minus sign? I add v0 to both sides, and I get an equation. V equals v0 plus at. Some of you are looking at me like, why am I doing that? Others of you realize that if an instructor ever pounds his foot, it means you better memorize that. Hint, hint, hint. Okay? By the way, it's not enough to memorize the equation. You've got to memorize what the equation applies to. Constant acceleration. If the acceleration changes, that equation does not work. Follow along with me, guys? Great, fantastic, let's do more. Some of you are like going, yeah, let's. The rest of you are going, no, not. If we take a look at the velocity versus time graph, you've seen this one before. That was the on-ramp, remember? 30 miles an hour to 60 miles an hour. What we saw was in order to find the total distance traveled, we had to find the area underneath the curve, underneath the line. And it turned out to find the area was real simple. All we had to do was figure out what is the area of delta x1, which is how far the object would travel if it was not accelerating, just moving at a constant velocity, and the area delta x2, which happens to be how far the object would travel in addition because it is accelerating. Delta x1 is equal to v0 times delta t. Delta x2 turns out to be 1/2 delta t times v minus v0. That's what we got from the previous lecture that we had on Monday. Now to find the total, all I got to do is add those two together. And that gives me delta x equals v0t plus 1/2 t times v minus v0. Wow, that's an alphabet soup, isn't it? It's not that bad. Here's what we're going to do. We're going to simplify that a little bit. Because in the previous slide, we had an expression which involved acceleration. Our expression was v minus v0 equals at. So what does that mean? That means what I can do is take that v minus v0 and replace it with at. And that will give me the expression delta x equals v0t plus 1/2 t times at. I can simplify that one a little bit, can't I? Yes, I can. All I got to do is multiply the t's together, and I get the expression delta x equals v0t plus 1/2 at squared. Now, I know a batch of you memorized that equation. But now you know where it came from. Now you see where it comes from. Okay? Any questions so far? Go ahead. No. It has to be. The question is, can this be for a non-constant acceleration? And the answer is no. The reason why is if the acceleration is not constant, you would not have a straight line on the velocity graph. That line would be curved. That means you could not find the area with the triangle. So this only applies when the accelerations are constant. That's actually a very good question. I got to keep stressing that. Okay? Ready? Yes, sir. Can I pull the t's out? Good question. Can I cancel out the t's? The answer is no. The reason being is while I have in the 1/2 at squared, I have 2 t's as factors. And in the v0t, I have a t as a factor. But on the left-hand side of the equation, there is no t factor. It's just delta x. So I can't cancel out a t. Okay? If delta x was 0, if the change in the velocity, if the change in position turned out to be 0, then I could cancel out one of them. Okay? But that's definitely not the case in this case. Any other questions? Okay, that's reasonable questions. I'm glad you're asking. I want to make sure that we are clear on all this stuff. Okay, let's do another one. This one's going to be a little bit fun. This is where we're going to play a little bit of geometry. Okay, let's take a look at that top rectangle. When I'm talking about the top rectangle, I mean the rectangle that starts at V0, goes up to VF, goes across to delta t, comes back down to V0 and back across. Let's look at that rectangle right there. wouldn't you say that the delta x2, this shaded area, is the same area as the entire rectangle? Does that make sense? I'm sorry, let me back it up. Wouldn't you say that it would be half the area of the entire rectangle? Yes, it is. Yes, it is. Okay, great, fantastic. Then doesn't that mean I can make another rectangle that starts at here and goes across like this? And wouldn't that have the same area as delta x2? Yes, because all I'm doing is I'm just changing where the half line is. Instead of making a triangle, what I'm going to do is I'm going to go halfway between VF and V0. Okay? How do I find that number? No. How do I find the number that that line is at? Halfway between VF and V0. Yes. It would be the average, wouldn't it? You want to test on that. If VF is 40 meters per second and VO is 20 meters per second, then halfway in between would be the average of the two. 40 plus 20, which is 60, divided by 2 gives you 30. So it turns out that the height of this red rectangle, of this bold rectangle, is going to be the average of the two velocities, which we calculated by V plus V0 divided by 2. Okay, you with me so far still? Okay, why am I doing that? Because here's the fun part. The bolded red rectangle is area delta x2. The rectangle underneath is area delta x1. But what am I trying to find? I'm trying to find the distance that the object traveled. I'm trying to find the sum of the two, right? Why don't I just go ahead and find the sum of that, find that rectangle there, where the base is the time and the height is the average of the velocities. Ta-da! Now we got it. And so what we have is another equation. Delta x is equal to 1/2 v plus v0 times t. Okay? So far, so good? Not too bad. Notice I built that one just by pure geometry, right? Now I'm going to build one with pure algebra. Okay, so how do we do it with pure algebra? Simple. We're going to start off with that expression, delta x equals 1/2 v plus v0 times t. What I want to do this time is I want to get rid of the time function. I want to get rid of the t. Okay? That means I need to replace it with an expression. So let's go back to the very beginning from the acceleration graph. From the acceleration graph, we had the expression v minus v0 equals at. So far, so good? Now, I want to get rid of t. So I'm going to take that second equation and solve it for time to give me time equals v minus v0 divided by a. All right, all good. Since I want to get rid of t in the first equation, I just take that fraction and plug that into the first equation, and that gives me 1/2, delta x is equal to 1/2 v plus v0 times v minus v0 divided by a. Okay? I'm not making any fancy steps along the way. I'm just doing everything by the numbers, one step at a time. Okay? But now I do have to clean it up. I want to get rid of the denominator. So how do I get rid of that denominator on the right-hand side of the equation? Multiply by 2a. So I get 2a on the left-hand side, 2a delta x. And on the right-hand side, I get v plus v0 times v minus v0. Okay, oh math geniuses. What is that expression on the right-hand side? Right, that is a difference in squares. Remember your binomials? Okay, so that means 2a delta x equals v squared minus v0 squared. And again, I want to get rid of the minus sign, not because it's necessary or anything like that. It's just to make it easy to memorize. So by getting rid of the minus sign, I get the equation v squared equals v0 squared plus 2a delta x. Now, again, you're looking at me, some of you are looking at me like, why am I going through all of this mess? And the answer is because these equations are the equations you come up with every time you use those velocity time graphs and acceleration time graphs under constant acceleration. These four equations, v equals v0 plus at, delta x equals v0t plus 1/2 at squared, delta x equals 1/2 v plus v0 times t, v squared equals v0 squared plus 2a delta x. Every single one of those equations come out of that. That is my mathematical model for constant acceleration. Following along now, guys? Oh, by the way, what about constant velocity? Does this work for constant velocity? Yes, it does. Because in constant velocity, what's the acceleration? So if the acceleration is 0, the first equation becomes what? V equals v0. In the second equation, what does the second equation become? Yeah, all we need to do is read across. Delta x equals v0t. And then we can keep going. Every time we replace a with 0, we end up getting with either v equals v0 or delta x equals v0t. Following along? So constant velocity is just a special case of the constant acceleration motion. So if I'm talking about constant velocity, my model is real easy. One equation, delta x equals v0t. If I'm talking about constant acceleration, my model is now 4 equations. You're looking, now comes the question is, well, why do I need 4 equations? What purpose of the 4 equations are? Well, let's take a look. How many variables do we actually have? In the first equation, we get the variables v, v0, a, and t. In the second equation, we add the variable delta x. But then we got v0 and t and a. And in the third equation, we got v, v0, a, and t, and so on down the line. With me here? Here's a hint when you're doing constant acceleration. If you're doing constant acceleration, you will be using all 5 of those variables. So if you recognize that there is a constant acceleration, you make a table of those 5 variables. Delta x, v, v0, a, and t. Some of them you're going to know, some of them you're not going to know. How many of them do you need to know in order to finish the table up? Nope. Nope. Sounds like Monty Python there. 1, 2, 5. No. No. 3. Okay. No. Okay. Let's take a look. First equation, how many unknowns do we have? How many variables do we have? 4. So how many variables do we need to solve that first equation? 3. If I know 3 of the 4, I can solve for the unknown. In each one of those equations, there are 4 variables. That means if I have 3 of the 4, I can solve for the unknown, correct? That means I only need 3 of these 5 variables, and I can solve for the other 2 by choosing the right equations. Well, how do I know which equation to choose? Well, there are 2 ways of looking at it. One way is look at your table of knowns and unknowns and find the equation that has the variables that you know plus the variable you want to find out. That's one way of looking at it. Another way of looking at it is take a look at each equation, and you can see each equation is missing a variable, isn't it? One of the 5 variables. This equation does not have a delta x. This equation does not have a final velocity. This one does not have an acceleration. And this one does not have a time. So if you know 3 of the variables, but you don't know 2 of them, one of them you don't care about. So you grab the equation that does not have the variable that you don't care about. So for example, if you know the initial velocity, the final velocity, and the acceleration, and you want to know the distance, do you need the time? Or you don't care about the time? So you would use the 4th equation, because the 4th equation does not have the time term in it. Does that make sense now, guys? Okay. You'll have plenty of time to practice that on the homework that's due on Friday. But now comes the interesting part. See, I don't have to just solve for one motion. You got to remember that motion can change. For example, a car speeds up, then travels for a distance at a constant velocity, and then it slows down. Is there one set of equations that solves for all three motions? No. I have to take those three motions, break them up into three segments, model each of those motions, and use the information from one to go to the other, and so on down the line. That's kind of like the airplane problem, the airplane touching down and coasting. We take the information from the first part and apply it to the second part. Okay? Another thing is what happens if I've got two objects moving that are related to each other. Such as this. Two hockey players are on the ice. Player A is standing still. Player B is moving at a constant 5.5 meters per second. B passes A, and then 1 second later, A starts chasing B down. If A accelerates at 1.5 meters per second squared, how far does A travel until it catches B? How long does it take? And how fast is A going? You can solve this. What might help might be a picture, yes? Okay. Well, what's happening is we have the hockey players. We've got A here, and we've got B here. At this point in space, they coincide with each other. B is going to have some initial velocity. I'm going to call it V1. What's the initial velocity for A? 0. He's standing still. So B passes A at that point, but A is standing still. So that means B travels to this point right here. I'll call that one x1. Okay? So B travels to this point right here. And at that point right there, when the time is equal to 1 second, that's when A starts moving. When A starts moving, A will have an acceleration. So B is at this point, A is at this point. Then what ends up happening? When they get to this point right here, A is going to overtake B. A is going to have a velocity, which I'll call V, and B is going to have a velocity, which I will call V1. My question for you is, what is that total distance? How long did it take? And how fast is V? Why don't you go ahead and break up into some groups and see if you can work out some strategies on how to solve this particular problem. Because this is the first exposure to a certain type of problem. Guys, there's a homework problem where you have to answer the question on whether or not somebody's going to rear-end a truck. That's in one of the homework problems. And it involves two vehicles moving, one with a constant velocity and the other with a constant acceleration. Okay? So how are we going to model this? How are we going to do this? Well, first off, let me give you a little bit of an insight. Let's take a look at the table of knowns and unknowns. I've seen a number of you do that. Good. It's a good way to get organized. We know that player A, is starting with an initial velocity of 0 because he's starting from rest. We know that player A is accelerating at a rate of 1.5 meters per second squared. We do not, however, know how long it takes for player A to catch player B. And that's why delta t is going to be t. We don't know how long it's going to be. So we're going to assign an unknown to that. Okay? So far, so good? Now, let's take a look at the motion for player B. Now, player B is undergoing a constant velocity motion. We know the initial velocity, which is the overall velocity for player B, is 5.5 meters per second. We also know that player B is going to be skating for as long as player A plus 1 more second. That's where that time delay comes into play. Okay? Now, what that means is we have two types of motion. Player A is a constant acceleration motion. Player B is a constant velocity motion. That means the equations for player A would be the constant acceleration equations. The equations for player B would be the constant velocity equation. You see where we're going here, right? Those are the tools we're going to use in our toolbox. We have to recognize what's the problem, and then we grab the tools appropriate to that. Now, let's make a position graph, and it might clarify some things a bit. And then you'll see what I'm talking about by the time and the distance and all that other stuff. On our position graph, we're going to go ahead and say at the origin, player B is going to be moving, okay? The origin is going to be where player A and B both are at the beginning when player B steals the puck. Player B is going to move at a constant velocity, so what should the line look like? We're looking at a position versus time graph. It'll be a straight line with an upward slope, so it'll look like that. That's player B. Now, what about player A? What is player A's line going to look like? It's going to have a curve to it. That's right, because the velocity is changing, which means the slope of this position graph will change. Where does line A start? At about 1 second later. So at that point right about there, there's your time delay. There's your 1 second delay, because remember the x-axis is time. And we see that the slope increases as A moves. That means his speed is increasing until we get to this point right here. At that point right there, the intersection of those two lines represents that A and B are at the same distance from the origin. So A and B are traveling the same distance. But take a look at the steepnesses. We see that the slope of B is less than the slope of A at that point. That means A is going to be traveling faster than B. And that makes sense, because if A is speeding up the entire time he's skating, then it would make sense that when he overtakes him, he's going to have a faster speed. So far, so good? New? Anything new, unusual? All of this is that prep work I keep talking about. Okay? So, let us now make the equations that model the motion. Player B is easy. Player B is moving at a constant velocity. What's the equation for constant velocity? Constant velocity. What's the equation for constant velocity? Initial velocity times time. Velocity times time. Distance equals velocity times time. What I'm going to do in this case is I'm going to substitute. I called V1 the velocity of player B, and I'm going to add 1 second. So what T gives me is the time that A is skating. B is skating for the same amount of time plus 1 more second. All good there? So we see where that equation is coming from. Okay, what about for player A? Player A's motion is constant velocity, it's constant acceleration with no initial velocity. So the question becomes, which equation do we want to use? We've got 4 equations. Which equation do we want to use that might apply in this case? Let me go back here. Let me step back. We know when we have constant acceleration that there are 5 variables. Our 5 variables are distance, delta x, initial velocity v0, final velocity v, acceleration, and time. What do we know for player A? We are given the acceleration. What else are we given? The initial velocity. We do not know delta x, we do not know the final velocity, and we do not know the time. Okay? That means I got to look someplace else to find one of those variables, or maybe 2 of those variables. What's the someplace else? What's the other place? Player B's motion. What can I get from what does player B have in common with player A? Time is going to be in common, correct? What else is going to be in common? The position, because they're both going to skate the same distance. So let's make a distance equation which has time. And the distance equation that has the time for under constant acceleration is going to be delta x equals v0t plus 1/2 at squared. Or in this case, delta x is equal to 1/2 at squared, since the initial velocity was 0. Okay? Why am I doing that? Because if I take a look at those two equations, how many unknowns do I have in those two equations? 2. 2 unknowns. I don't know t and I don't know delta x. Okay? I do now have 2 expressions for delta x. So if equation 1 equals delta x and equation 2 equals delta x, what can I do? Set them equal to each other. So I can write delta x on the left-hand side is 1/2 at squared. Delta x on the right-hand side is going to be v1 times delta t plus s1, plus 1 second, excuse me. You see where we're going here, guys? How many unknowns are in that equation? 1. And now you see, by making this table, I can see what's my unknowns that I can get from the other motion. What are the unknowns that the other object has that's in common with this object? Then I can maybe set up some equations that are equal to each other that way. It's a little bit of a work, I agree, but a little bit of practice, you'll get it down. Okay. How do we solve this problem? We do not plug in. We cannot plug in because we do not know t, do we? Correct? All right, so that means we got to solve for t. So let's get t by itself. Can we get t by itself? We can. Let me go ahead and distribute the v. Let me get rid of the 1/2 by multiplying both sides by 2 and distribute the v1, because I've got to distribute the v1 to what's inside the parentheses, yes? Okay, if we do that, then we get the expression at squared equals 2v1t plus 2v1 times 1 second. Now we're solving for t, right? What do I do next? No. Because if I divide by a, then I'll get t squared is equal to some expressions. But I'll still have t on the right-hand side. What else can I do? If I divide by t, that doesn't give me anything. Nope. Here's the problem. If I divide by t, I can cancel a t on the left-hand side. I can cancel a t in the first term, but I can't cancel a t in the last term, which means I can't cancel out that unknown. Yes? No. How can you substitute? It's only one equation with one unknown. We know the only thing we don't know in there is t. What do you think? Yes? Excuse me? No, you can't factor out the t. Because there is no factor for t in the third term. In the 2v1 times 1 second, there's no t term in there. Okay? The time that's in there, the 1 second, is different from the time that A and B take to travel. So you can't cancel that. Yes? But I don't have a 2v. Can I factor out 2v1? I don't have a 2v1 on the left-hand side. Yes? No. Because if I subtract 2, again, I cannot subtract 2v1. I've already distributed it out. Yes? If I divide by 2v1, I can't cancel out because I don't have a 2v1 term in the at squared. If I divide by t squared, I still can't factor them out. Square root of t squared doesn't work because I've got a t on the right-hand side. Come on, guys, this is Algebra 1 stuff. You're just avoiding the obvious. No. No. No, we don't. We're not going to. We can't add a. We can't do any of that. We can't do that. We cannot do that. We cannot solve for t by simply manipulating. Yes? Excuse me? No, because you still don't know t. Even if you plugged in values, you still wouldn't be able to find t. Or maybe you will. The problem is, how do you get t by itself? How do you solve that type of equation for t? Yes? There we go. What type of equation is that, guys? That's a quadratic equation. That's a second-degree polynomial. Do you see it now? That's a second-degree polynomial because we find the whole thing equal to 0. We get at squared equals minus 2v1t minus 2v1 times 1 second equals 0. That's the standard form for the quadratic equation, isn't it? You see? You guys were avoiding it is what you were doing. You're trying to find everything to do but solve for a second-degree equation. So what do we need to find now in order to solve this with the quadratic formula? What do you mean as much of the number? We need to find the coefficients, a, b, and c. Now we do substitute the values, because I need to know those values to get the coefficients a, b, and c to plug into the quadratic formula. So by substituting the values, I get a is 1.5 meters per second squared, b is minus 11 meters per second, and c is minus 11 meters. You see where we're going here now, guys? We now have it in the form that we can solve by using the quadratic formula. There's a reason why there's a math prerequisite for this course, guys. See where we're going? Oh, and by the way, do you remember the position time graph? We had a line, and then we had a parabola. And the solution is going to be where the line intersects the parabola. How many places does a line intersect a parabola? 2 places. You following along now, guys? Now everything starts to make a little bit more sense. So when we do that, we apply the quadratic formula, and we come up with 2 roots, 8.2 seconds and negative 8.9 seconds. Are they both right? No. Because while they're both right mathematically, from a physical standpoint, any negative time means time before the problem started. Okay? Well, before the problem started, A isn't moving. So therefore, it does not work. So we drop the negative root and use the positive root, and now we know the time it takes for A to travel the distance, 8.2 seconds. All good now? Now remember my table on A. I had the initial velocity and I had the acceleration. Now I have a third form. I now have the time. Now that I have that, I can finish the table. I can find the acceleration by using v equals at, which is just v equals v0 plus at. Since I know the time is 8.2 seconds, I know what the acceleration is. I see that he's traveling at 12.3 meters per second when he overtakes B. The next question is, how far did he travel? Well, that's easy. I just go back to my distance equation. Delta x equals 1/2 at squared. Since I now know the time, I can plug that number in, and I come up with the 50.3 meters. Does it make sense that the skater is going to take about 150, 160 feet to catch, that A is going to take about 160 feet to catch B? Maybe a little far on a hockey rink, but not on a pond, right? Those of you from up north, right? Does it make sense that A is going to be traveling at about 25 miles an hour when he overtakes B? You can go pretty fast on skates, so yeah, that's reasonable, okay? So you're following along here. Not every problem is going to end up with a quadratic. But when you have two objects that are moving, and you have only two unknowns on your constant acceleration side, find out what it has in common with the other object and see how I can set up an equation between the two. Is the time going to be the same? Is the distance going to be the same? Velocities generally tend not to be related to each other. So the velocities aren't going to be the same. Okay? Not unless there's a physical thing happening like I'm riding a train. Then me and the train have the same velocity, right? Okay. Any questions? Any answers? You got homework to do. Homework number 5 gives you a chance to practice this stuff. If you've seen all this stuff before, if you started homework 5 already, great. This will probably help fill in some of the holes. If you haven't started homework 5, you got yourself a long couple days ahead of you. So I will see you guys when I see you next.